Everyone, my name is Xiangyu from Arizona State University. Today, I'm going to give a talk about our project Self-Aware Program Analysis in stableKanren. Today's talk consists of 5 parts: introduction, preliminaries, problems, identify monotonic programs, conclusion, and future works. Let's get started with mini-Kanren. Mini-Kanren shows a natural way to extend functional programming to relational programming by providing 3 basic operators: equal for unification, flash for existential, county for disjunctions. The reasoning capability behind mini-Kanren is monotonic reasoning. stableKanren extends mini-Kanren to non-monotonic reasoning by providing 2 more operators: notto for negation, defino for goal definitions. And they all come with one unique run interface to run the query from the user input. Notice here we use the blue to indicate the interface or the operators coming from the mini-Kanren, and the orange indicate the operators and interface coming from stableKanren. The specialty about stableKanren is this non-monotonic resolution approach. So let's take a detailed look into it. So for the monotonic program in mini-Kanren, it has the optimal substructure properties. Therefore, the mini-Kanren runs will obtain the partial answers, and this partial answer is guaranteed to be part of the complete final answers. However, there is no such property, optimal substructure property, for non-monotonic reasoning programs. Hence, the stableKanren run continues the non-monotonic resolution to make sure, okay, this partial answer set is the complete answers. So there are 2 problems in the current run interface in stableKanren right now. Firstly, monotonic programs with infinity answer set answers could not produce an answer under stableKanren's run interface. Secondly, apply non-monotonic resolution to monotonic programs will took longer time to produce answers. So there is one simple solution. Is like, okay, how about we use the run interface from the mini-Kanren as the run partial along with the run in the stableKanren of monotonic programs, so it will produce the answers in a faster way. However, this requires the expert knowledge from the users to decide, okay, which interface to use, run or run partial. We want a smarter run interface in stableKanren that can identify monotonic programs. So let's take a look at some preliminaries. First, we will look into the categories of normal programs and the mini-Kanren. So to get into a normal logic program, let's take a look at the definite program first. A definite program clause is a clause of the form A will imply by the B1 ... Bn as a kind of the bodies, where A, B1, Bn are all atoms. And a definite program is a finite set of this kind of the program clauses consist together. Similarly, we will have the normal program definitions. The one special thing about the normal program is like, okay, here we have a not keywords in front of the bn plus 1 till the bm. Here not means the negation, and instead of everything is the atom. Here you just call it literals. Okay, so a program clause will consist precisely one atom A as its consequence. A is called the head, and the B1 ... Bm is called the body of the program clauses. So here are some categories of the normal programs. In a normal program, set of atoms named unbounded set can help us categorize the normal programs. We given a normal program, the atoms inside unbounded set only cyclically support each other by forming a loops. Therefore, we're using these loops and the negations, the relation between the loops and the negations. We will have informal categories of the type programs, stratified programs, and the normal programs. So for the definite programs, there's no negation in theirs. Then comes to the type programs, we will allow negations, but there's no loops in the programs. Then we go to the stratified programs, where, okay, we can have the negation and the loops, but all loops do not contain any negations. Lastly, we will get the normal programs, where there is no restriction. So for example, we can have a loop over negations. We will look into the detailed examples later. So mini-Kanren is basically support definite programs as the definition we see here, and with all the operators, equal, flash, county, and run. we can have a example program to distinguish to tell, okay, to run the query on if these two lists are reversed to each other. Reverse row basically saying, okay, the XS and SX, they are reversed to each others. So one simple query is, okay, you can ask reverse row relation, is these two empty lists reversed to each other? So the answer return succeed, which means, okay, they are reversed to each other. Or if we give a list of the same, like 1, 2, and 2, 1, and ask, okay, does these two reverse to each other? It also return true. Otherwise, like 1, 2, 1, 2, give us false. This what kind of examples? And yes, the reasoning capability is the monotonic reasoning. Now, stableKanren is the non-monotonic extension of mini-Kanrens. Okay, so we can stableKanren can support normal programs with all the new operators, lotto and the define nodes. So one example is like, okay, the two-persons game where we give a chessboard and each player move the peg on the board. If the winning condition is decided by, okay, your opponent has no more move, so you are in the winning conditions. So the program we can written in stableKanren to represent the two-person game like this. And we can also like run a query to find out all the winning condition for us. For example, we start from C, we guarantee us the winning position. So the reasoning capability behind stableKanren is non-monotonic reasoning. Okay. Now we have this kind of relations: mini-Kanren, stableKanren, monotonic reasoning, and non-monotonic reasoning, and the categories of normal programs. We need to connect these two together. So first, definite programs is supported by mini-Kanren. It's monotonic. Then the type programs was supported by stableKanren because the lotto we allow the negation in there is also monotonic. And the stratified programs where, okay, we have a negation and the loops that does not contain each other's, it's also monotonic. And lastly, normal programs supported by stableKanren is non-monotonic. stableKanren handle this loop and the negation within the definer macros. So it can reason about this contradiction, and it handles the monotonicity, non-monotonicity within the run interface. So we have definer and the run here. Definer basically taking the positive input from the users using a complete macros to create the negation, negative counterparts of it. And the definer will wrap everything with the local tabling handling, some hidden goals, wrap everything to be one unique new Go functions. And the run interface here, we have the mini-Kanren run and with our non-monotonic resolutions. So all the things defined here by the definer will add into these program rules and be used by the non-monotonic resolution later. Okay, so this approach has two problems as we mentioned before. Okay, here we are still using the same reversal examples to see, okay, if these two lists are reversed to each others. So here, this is the mini-Kanren version. See here, we only use define, okay? And okay, it belongs to definite programs. It's monotonic. So if we run this query in using mini-Kanren's run interface, so this is blue colors, it will give us a result saying, okay, it's true. These two empty lists are reversed to each others. And if we run a query, okay, how about we generate all possible lists reversed to each other, then we know there are infinity number of these things. So here is the problem, the first problem, where for definite programs, it has infinity models. And if we try to run in stableKanren, so for example, here right now we are using the definer, the orange color, to define this relation. The rest are the same. We're just using the definer interface, and they use the stableKanren to run on getting one answers, which it was producing a result in mini-Kanren, but it falls into infinity groups. So this is our first issues. Then the second one is, okay, how about we try to run some program on the stratified programs. Here is one example, final SCC. You will consider the strongly connected components SCCs in these figures. Then we will call an SCC is a final SCC if the only nodes reachable from nodes that in that SCC are others. Now, given a node, we want to find all nodes that are reachable from that node in the final SCC. So for example here, we have one strong SCC CDE forming one SCC. and the A goes to C, D, E. C, D, E are the final SCCC of A, and same as well to the B. So basically, it's all the leaf SCCC are considered as the final SCCC. So this problem can be encoded in stableKanren like this. And if we try to run using like the run partial things we mentioned, it goes very fast. It only takes like 0.01 seconds to produce the answers for 100 pairs. But using the stableKanren run interface, it would took like 32.666 seconds on the same machines. So this is not ideal. So run partial is very simple. Like I mentioned, we just removed the non-monotonic resolution, like the part we show here in orange colors. We just remove it as a run partial. Now, without these checkings, then the user can say, okay, it's the monotonic, I will use run partial. It's the monotonic, I use run partial. Monotonic, I use run partials. But for the non-monotonic versions, we still need to use a run interface. And this is not ideal, as we mentioned in the introduction. So we want the run interface can have some ability to identify these like kind of like monotonic programs. So you can decide, okay, I would apply the non-monotonic resolution or not. So it basically is like, okay, we try to identify the negations and the loops and the layer relations. Okay, does the loops contain any negations or not? So let's take a look at the first problems where, okay, we try to run the definite programs with infinity models in stableKanren. So here we try to create a macro called has negations, ? Because the syntax of stableKanren consists only 5 elements here. It's the go functions, equal, fresh, condy, and the nottles. Therefore, for a definite program, we only focus on whether this program will consist of negation, these nottles, or not. Therefore, a syntax analysis using macro like has negation can achieve our goal. So the macro, we can write it, as I mentioned, we only have 5 elements, so we focus on these 5 things, nottle, condy, fresh, and the go function. And because equal is the basic levels, we don't need to worry about that. So this has negation. When we given a program and using this keyword nottles, it will say, okay, it's true, it has negation inside. Otherwise, for example, condy and the fresh, it's just compound formulas. We just iterate through it using the same has negation until we reach the base case, like the go function. We only have one go without the nottle keywords. This is false. There's no negation inside. Or we just or everything together to tell it can tell us, okay, is there any negations in there? So by using this has negation interface, okay, we plug into this process when we try to add the predicate into the program rules. Here, okay, we're embedding a has negation to define no, so that stableKanren can identify these definite programs. So right now, it will only add the PX that has negation inside to these program rules. If there's no negation, we will not run the non-monotonic resolution on it. So in this case, okay, our updated run interface is capable of handling this kind of the program now. And the same thing, this updated interface can handle the normal program for sure. And right now we need to taking care of the stratified programs in stableKanren. Now we not only just need to identify the negation, we also need to know where is the loops inside. So this requires more analysis of the relation between the go functions. So for example, a loop could be a self loop involving only one go function. A loop could also contain more than one go functions. For example, this is the self loop. It contains only one go functions, cut here. It basically is the paradox saying, okay, if I try to cut hair, I cannot cut a hair. You try to make true and false at the same time, which is impossible. So this is unsatisfiable. So this is a self loops. And then we can also have another loops to generate the combinations. So here the pick and the free, they basically forming loops over this negation. Like you pick, it will not free, and if you want to free, it will not pick. Okay. So traditionally, a logic programming solver will create a dependency graph for such a purpose. So let's look into another, the final SCCC problems here. So for example, here we know we have 1, 2, 3, 4. We have 4 goal functions: edge, reachable, reducible, and fully reduced. And every time if there's an auto, we will draw a negative edge between the 2 goal functions. If there's no auto, we will draw a positive edge. So this is the dependency graph looks like. Okay, for example, from fully reduced, we'll have the positive dependency to reachable, and we have negativity dependency to reducible. Okay, and see here, there's one loops, but it's the positive loops under the reachables. Okay, now, but we don't want to, for example, like here, constructing a dependency graph with an algorithm. This is a non-functional approach, and we don't want to use this non-functional approach. We want something purely functional. And here we notice like, okay, we already done in building stableKanren by wrapping a new code snippet around through the definer macros. Then we implement, in this way, we implement the stable model semantics for negations and loops. How about like, this is the definer interface we already saw before in the preliminary parts. Now here we may wondering, okay, how about we're using the similar ideas. Okay, we use a similar idea to generate 2 smaller queens with different semantics for negations and loops. So for example, here, this P of X, we have one positive twin, P plus, is in different colors of the local tabling and the loop handlers, which means, okay, here we may have some different semantics, and we're still using the same P of X from the users. And the same thing here. Okay, the P minus is also the different semantics of the loops and the negations. Okay, now back to the final SCCC example code. So this code, then we will try to create the negative twins. Okay, the smaller twins are created from this user input with the suffix plus or minus. These twins will ignore the parameters and only need to capture the relationships between goal functions. Okay, so this is the twins look like. So here, for example, the edge, we ignore the parameter x and y, so nothing in there. And because here inside we all like unification means, okay, you always succeed. And this is the edge because we try to generate the negative twins, so it's edge minus. So same thing for reachable, we drop the parameters, but we only keep the overall structure of these the programs. So for example, edge will become edge minus, but flash, we don't care about the parameters there. It's just edge minus and the reachable minus. It's just like the dependency graph, but it's self-executable. So in this way, so here is one code snippet from the creating the negative twins. So here the color in maroon is like we drop the unnecessary parameters. We don't want it, and we only append the suffix to it. So if it's a positive twin, the only difference is that here we replace the minus sign with the plus sign. So here we ignore all the parameters, and this is adding the suffix. Okay, now we have this twins now. So now the stableKanren is able to perform the self-aware program analysis. Since the 2 twins have different semantics for loops over negations, we can use them to identify monotonic programs now. So remember these 2 twins here, the different colors indicate they have different semantics for the loops and negations. So the twins of the monotonic programs will always produce identical results. So for example, this P plus and the P minus, if they are monotonic, they will produce the same result. And the twins of the non-monotonic programs produce different result. If it's not monotonic, the P plus and the P minus will be different. The result will be different. Then we need to use the non-monotonic resolutions. Now, if we add these things into the run interface, the run interface becoming more smarter. Like we unify with everything with the run keywords. No more run partial needed. So the conclusion and the future work. So in conclusion, we fixed the 2 issues of running monotonic programs in stableKanren at the syntax levels. However, there are still some issues at the runtime level. This monotonic detection still needed to add it into the stableKanren run interface. So let's go back to the Revoro examples. Like for example, right now, if we already fixed it. So the new run interface in maroon colors can produce the answers for the reverse rows. However, right here, the maroon run interface can produce the answers for the reverse row now. However, if in the same environment, you also have the unsatisfied program as we saw before, the cut hair here. Right, currently the run doesn't know, okay, these two that's not related to each other. It will still try to do the non-monotonic checking on this part and leading the query to failed. So right now, if we have the reverse row and the cut here in the same environment, the run will be unable to produce the answers. So here is the thing we try to fix later. Thank you so much. Thanks for your time. I will take some questions from over the Zoom. Thank you.